absolutely guarantee it. This is the most fascinating thing that I've seen, possibly in my entire life. Like, this is something that I looked and I decided, I want to try to figure that out. I want to figure out how this is working, and this inspired me to go into physics. What you're looking at here is one of the biggest mysteries in classical physics. It's called turbulence, fluid turbulence, and it's something that we never have figured it out. We can't write down a nice solution for how this works, and it's a big problem. It's in everyday life, we find that we can't solve this amazingly intricate fluid mixing. So, all right, back to reality. Sorry. So what I'm talking about is turbulence, and everyone is probably thinking right now, well, turbulence is something that I experience when I'm flying. You know, when we're going around the Alps and all of a sudden you go boom, and you're like, whoa, okay, so your plane drops 10 meters in the sky, and you're like, okay, that is turbulence. And you are correct, that is an expression of turbulence. But it's actually a description of a much larger class of fluid flows. It's a description of when fluid behaves essentially unpredictably. So if you see this smoke here, there's this point where all of a sudden it goes from behaving really nicely and smooth streamlines to getting this really chaotic and twisted structure. And it looks like it's completely random, but when I say it's unpredictable, I mean it's unpredictable by humans. Computers can figure out how this works, and also we have equations for what that fluid is doing. In fact, this equation, this is the Navier-Stokes equation, and I promise it is the only equation in this physics talk. Trouble is, we can't solve this equation. We can't write down a nice, x equals y coming out of this. And this is $1 million problem. It's literally $1 million problem. If you can even prove that there is an answer, you don't have to say what it is, but if you can prove that there's an answer to that question, you will be given $1 million. It is the Millennium Prize problem. And what you're seeing is chaos. So not chaos in the sense of, I haven't cleaned my kitchen in a few days and oh my goodness, there's nothing I can do for it. Chaos in the sense of a physics term that when you have something that starts in a particular position, a particular state, and then evolves, and you bump it just the tiniest amount, if it's a chaotic system, it ends up being completely different. And when this happens in a fluid, you have lots and lots of different fluid particles, and they're all acting in this very sensitive to initial conditions state. And they then self-interacts, and you have all of these large amplified motions that then cause this roughness that you notice in your coffee cup. You notice it when you're flying. And this is something we can't solve. It's a big problem in physics. Hopefully this is what we can sweep under the rug, surely. Maybe this is 1% of fluid flows, and the rest of it we just don't have to worry about. But actually, unfortunately, it is most fluid flow. The case where that smoke was having nice streamlines before, that was the exception, not the rule. You see turbulence just about everywhere you see a fluid. It's really nice to see it when there's an interface or something where you can tell what's going on. You can see it in this spray coming off this wave here, but also in the twisting and turning of a leaf. Have you ever tried to predict how a leaf falls down from a tree? It's almost impossible to do, isn't it? And the reason for that is the bumpiness, the roughness of the airfield that is below the leaf. You also see it on planetary scales. This is one of the most famous examples of turbulence. This is the Great Red Spot of Jupiter. Turbulent flows they have so much power that they can shape the planets. And of course, you get it when you're flying. And maybe you can ask me later if you want to understand where the roughness comes from. It's sort of interaction with obstacles, but we'll save it for later. So all of this generation of vortices, this generation of this structure, this is really great for your coffee. I mean, who wants to have half of your cup be milk and half of your cup be coffee? No one really wants that, right? You want to have just milky coffee, presumably. So it's great. This is one of the more efficient mixing mechanisms that we know of. This is one of the most efficient mixing mechanisms in the universe. And if you stir it, actually, you promote these large extra vortices, and then you get incredibly quick mixing. This, for coffee, brilliant. However, it's really bad for fusion reactors. I realize this is a large jump of focus, but bear with me for a second. So fusion reactors are essentially how we try and replicate the conditions in stars on Earth. So stars, this is probably the one you're most familiar with, this is our sun. And essentially what you need to build a fusion reactor is you need to have tremendous amounts of heat. You have, to cause the fusion reaction, you need to smash particles together and they need to stick. Doing that requires an extraordinary amount of energy, which you find as temperature. To cause a fusion reaction to occur, you need to get to 150 million degrees Celsius, which, once you get to that point, like, the degrees, it doesn't really matter, does it? It could be Kelvin, it could be Fahrenheit, like, it's just an astonishingly large number. And compared to that astonishingly large number, everything else is cold. Your wall, even if you heated your wall up to 800 degrees, which is very, very warm and you'd cook a cake in a second, it would be very, very cold compared to the core of your star. And when you smash these particles together, you want to keep all of that heat inside, so that reaction keeps on going, so it keeps on sustaining itself. And so what you're trying to do is essentially like trying to put the heart of the sun inside a bottle, which is an astonishingly difficult challenge, but we've tried lots of different ways. This is in Germany, actually, top left. It's one of my favorite fusion reactors, which is possibly the nerdiest thing you'll hear all night. The Wendelstein 7X, beautiful piece of engineering. This is laser ignition. There's an amazing site in the States. This is something that we're building in France right now, which we hope will be the first one that ever actually works. And it also has inspired science fiction writers. This, if you recognize, this is Tony Stark, this is Iron Man. And if you look at what he's standing in front of right there, it looks an awful lot like this one, doesn't it? It's pretty much the same thing. This is the arc reactor in Iron Man 1. And it inspired a group of MIT researchers to build their affordable, robust, compact reactor that is completely not inspired by Iron Man, but they're totally lying. And it's a really cool design, actually. And the challenge is, the reason why we haven't gotten to work yet, is that starting a fusion reaction is a little bit like starting a campfire on a really cold, blustery winter day. And what you've got is you've got all of your fuel nicely stacked up and ready to go, and you strike a match, and then you put the match into the campfire, and you try and get your fire to start burning. And what happens is you get some of the wood catches fire, and then the wind picks up and it blows it out. And so you strike another match, and you try again, and strike another match, and try again. And you keep on doing this until you get a little bit of burning happening, but then a big gust comes along and blows everything out. In this situation, the fuel is the fuel. The fuel is hydrogen isotopes, and the heat that we're trying to achieve is 150 million, but the gusts of wind, that is basically plasma turbulence. The box of matches is the energy that we're taking from the grid. So what we're doing is we're striking so many matches that we might as well set the matchbox on fire. We're not getting energy out of this system. It would be easier just to use the energy as it is, rather than try and make fusion out of it. So turbulence is the thing that is stopping us from achieving this, so we have to devote a lot of attention to trying to figure out how it works. And to do that, we enlist some of the largest supercomputers in the world. We haven't found a good mathematical solution to the Navier-Stokes equation, so we write supercomputer code to try and get an approximate solution for it. And this takes I remember reading a number, which I think was 60% of the world's supercomputing powers, give or take 20%, because no one's quite sure what's happening. But 60% of the world's supercomputing power is devoted to solving fluid flows. So if we could find an analytical solution for this, it would be astonishing. It would completely revolutionize how we do computational fluid dynamics. And that is sort of what we do at Max Planck. We write supercomputer code, but we also look for analytical solutions. And we had a hint in 1941. This is the more technical section of the talk, but there is a very cool thing that comes out of this. You have these large eddies that you see here, and they feed smaller ones. And that balance between large and small, the balance between the large-scale motions that you're noticing and how it dissipates at smaller scales, this gives a very distinctive energy balance. And this brings me right back to my start, which is Van Gogh's Starry Night, which was painted in 1889. This guy, if you look at the pattern of light and dark in this painting, and you look at this energy spectrum that I just showed you, Van Gogh somehow managed to figure out that energy spectrum. If you do the analysis on this painting, you will recover that energy spectrum. Hundreds of years ago, he managed to figure out how turbulence affects the stars. And that's something we're still trying to do today. If we could, then we could make energy sources for generations. And that is what we do at Max Planck. If you're interested, then we are literally at the end of U6 if you're heading north, and we do tours. There's a Twitter handle there, and also an email address if you're interested, and that is me. Oh, also a large thanks to Turbulence team, that mesmerizing YouTube video. They have this section of simulations, and they're just fantastic, so I highly recommend checking them out. Thank you very much.